This video is about microphone sensitivity. It corresponds to sections 26.4.2 and 26.4.3 of the Applied Analog Electronics textbook. Let's have a brief refresher on what is going on with an electret microphone. We have got a variable capacitor that consists of the diaphragm and the backplate of the microphone. This variable capacitor is driving a junction field effect transistor. It is providing the gate to source voltage for that transistor. And what we're going to be interested in measuring from this field effect transistor is the current from the drain to the source. Okay, let's take a look at that gate to source voltage there. We've got a constant charge provided by the electret. That's the capacitance times the voltage across the capacitor. So that tells us that that gate to source voltage is the charge divided by C. Now the capacitance itself is proportional to 1 over the separation between the plates. It's just standard capacitor stuff. So what that tells us is that the gate to source voltage is proportional to the separation. Now, what does that separation do? It starts out as a fixed distance, but the change in separation is proportional to the change in pressure. When we've got a high pressure, we're pushing the two plates together. When we've got a low pressure, we're pulling the plates apart, so the constant proportionality may be thought of as negative. But basically, if you think of the thing as a linear spring, small changes in pressure produces a linear small change in the separation. So overall, that tells us that the change in the gate to source voltage is proportional to the change in pressure. That is, that this is a linear device. The gate to source voltage is linearly related to the pressure. Okay, what we're interested in though isn't the gate to source voltage. We've got no way to access that. What we're interested in is the drain current. And we did do a DC analysis to look at what the drain current was. And when we make the measurements, we get that the drain current goes up linearly for a while and then saturates. And that's with respect to the drain to source voltage. And what we're interested in is how does this drain current depend on the gate to source voltage. So we're interested in what's called the transconductance gain, G sub m, which is the derivative of the output current with respect to the input voltage. And I didn't give you in the book the detailed models for junction field effect transistors, but we've basically got two different regions here. In the linear region, GM is proportional to VDS, so that we've got no transconductance gain down here when we've got no voltage. As we go up in the linear region, the transconductance gain basically goes up linearly with the current and linearly with the voltage. In the saturation region, things are a little bit different, and G sub m is proportional approximately to square root of the drain current. But in the saturation region, the drain current is basically constant, and so the transconductance gain is basically constant. And that would mean then that the current, the change in current, is proportional to the change in the gate to source voltage. That's basically what this is saying. If the derivative of the current with respect to the voltage is constant, then we have a linear relationship. And in the saturation region, we would have that the derivative of the drain current with respect to pressure is approximately constant. And that's what we want, a linear response. Now the trouble is all this analysis has been proportionality. It's proportional to is proportional to. And this doesn't tell us, well, how sensitive is it? What is this constant? we need to know that in order to do any design, because it's not enough just to say it's linear. We have to know, well, how big a current do we get for a given pressure input. And to do that, we're going to have to look at the datasheet. Okay, here's a datasheet for an electret condenser microphone. Condenser, by the way, is an old-fashioned word for capacitor. So this is the same sort of microphone that we would be using, but it's a different model. I deliberately chose a different model than the one we're likely to use in the lab, so that you will have to go through the same exercise over again with different values for the microphone that you'll actually be using. Okay, where is the sensitivity on this datasheet? Well, if you look at the second line there, it tells you sensitivity. It tells you conditions and descriptions, and then it gives us sensitivity in decibels. Well, what we wanted to know was how many microamps, amps, whatever the units are, per Pascal, pressure units, did we have, because we were looking for the derivative of current with respect to pressure. All right, decibels is unitless. So how do we interpret decibels? Well, there's going to be a logarithm of a ratio, and this conditions and descriptions line, that column, tells us that 0 dB is, that's not an equal sign, it's an is, 1 volt per Pascal. So let's take a look at what that is telling us. We have got that 20 times log base 10 of x over 1 volt per Pascal, because the 0 dB is telling us what the reference here is, equals, and then the number there was a minus 38. That was the typical value. There's a plus or minus 3 to get the minimum and max values. All right, if we rewrite that, we can say that x is equal to 10 to the minus 38 over 20 times 1 volt per Pascal. And if I get out my calculator now, I get that is 12.59 millivolts per Pascal. That sounds great. We're done, right? We want millivolts per Pascal, but wait a second. I was looking for current output from this microphone. Millivolts isn't current, that's voltage. Something's wrong. And what's wrong is that they're not really telling you the characteristics of the microphone. They're telling you the characteristics of a circuit that uses the microphone. And in fact, it's a circuit that you've seen before. It's a bias resistor and a microphone. And they're telling you what's the voltage output from this circuit. Well, we need to know more about that circuit. What's the voltage up here? What is the resistance here? Because it is a current output device, so we need to know what they use to convert that current into voltage. All right, well, let's take a look. Let's go back to the datasheet and see if it tells us that. On that sensitivity line, it doesn't tell us anything about the measuring conditions other than the frequency is 1 kilohertz. And that's useful to know because at 1 kilohertz, it doesn't matter whether you're using dBA weighting or not. 1 kilohertz, the dBA weighting is 0 dB, so there's no adjustment needed for frequency. That's probably why they picked 1 kilohertz, so they didn't have to worry about, is it dB weighted, is it A weighted for the decibels, or is it not A weighted? Whether it is or isn't, at 1 kilohertz, it doesn't matter. Okay, we do have an operating voltage here, which says typically 2 volts, maximum 10 volts. So probably they were using 2 volts, but they might have been using something more. Then they say the output impedance at 1 kilohertz and 1 Pascal is 2.2 kiloohms. Now, it doesn't make any sense for there to be an output impedance of a microphone, because the microphone is a current device, not a resistance. But if you look at what's the Thevenin equivalent of that circuit we were looking at, well, the Thevenin equivalent of that circuit does have an output impedance, and the output impedance is just what that resistor R is. So this is telling us what resistor they used for doing the measurement. It was 2.2 kiloohms. So I'm going to write that down over here so when we switch back we can see it. And then further down they say sensitivity reduction. How much does the sensitivity reduce if we switch from Vs being 2 volts DC to 1.5 volts DC? Again, implying that they used 2 volts DC for doing their measurement, because if you switch to 1.5 volts DC, well, we would expect, if we stay in the saturation region, that all that would happen is, no. If we stayed in the saturation region, there wouldn't be any change in the sensitivity, because in the saturation region, the DC current stays the same. And what this is saying is that if we drop down at this point, we lose 3 dB. And I say dBA here, but at 1 kilohertz, the A doesn't mean anything. So this is saying that the 2 volts was kind of on the edge of the saturation. If we drop down to 1.5 volts, we'll lose some sensitivity. Okay. Frequency range, current consumption. Again, they give the current consumption 2 volts DC, and with a load resistor 2.2 kiloohms. So we consistently see that they've done all their testing, 2 volts power supply and 2.2 kiloohms. So we now know that we have this test circuit. Well, how do we convert this voltage sensitivity back into the underlying current sensitivity? Well, we know what sense resistor they were using. They were using 2.2 kiloohms. So if we just divide this voltage by the 2.2 kiloohms, we will get the sensitivity, the actual sensitivity in amps. So I'm getting that what we really have for sensitivity, the derivative of the current with respect to pressure, is 5.72 microamps per Pascal. Okay, so that's the sensitivity of this microphone, and I can use that now as long as I stay in the saturation region, so I'm keeping a high enough voltage across the microphone. I can change this resistor and just multiply whatever resistance I'm doing by this sensitivity for the microphone to get the volts per Pascal sensitivity output for the bias circuit. If I switch to having only 1.5 volts at the input here, I know that I've got to redo the calculation with 3 dB less sensitivity, because it's beginning to drop out of the saturation region at that point. Your microphone will have a different saturation region, different sensitivity, but the basic idea of it is the same. They will give you a sensitivity in decibels relative to some specific volts per Pascal sensitivity. And you've just got a unitless ratio here, and turning it around, dividing both sides by 20, exponentiating 10 to the power, will give you the sensitivity in volts per Pascal. And then you have to find out what bias resistor they were using, what resistor they was using to do the current to voltage conversion, in order to figure out what the underlying current per pressure sensitivity is. And that's really all there is to figuring out microphone sensitivity. It's fairly straightforward.